All right, this is a great review problem for rotation. It involves a lot of different ideas. So uh, the notice that they have triangular rods that they show in the problem, and it has a non-uniform linear mass density. So this is going to help us involve a little bit of how you calculate the moment of inertia from a simple integration. All right, and what they have is a hoop, and there's 3 spokes that are like that triangle inside of the hoop. So what we're going to do is take this piece by piece, and the overall goal, first part, is going to be calculating the moment of inertia of 1 rod, and then finding the total moment of inertia of the hoop with the 3 rods. Okay? All right, so the linear mass density, okay, shows that it's going to vary with the position, okay, in terms of the function x here. And so in terms of the overall lambda. So what you end up doing is you're going to use the basic definition, and this is on your sheet that you can use on the AP exam, your equation sheet, that the moment of inertia is the integral of r squared dm. Now, the goal is, all moments of inertia of any shape should be some constant k times like mr squared or m, l squared, whatever it's going to be. And in this case, since we're using one-dimensional, the linear mass density, we probably want to express, and that's in terms of x. We'll let our position r here also be expressed in terms of position x. All right. So if r is going to be our x, r is our distance away that any little dm is, so that'll be x in terms of the linear position. We're going to integrate x squared dm. So we just have to express dm in terms of, how does the mass also vary as a function of x. So dm is always the mass density, right, times dx. That'll give you the mass of any little element. So in this case, they give us a function for this, and they tell us it's 2m over L squared x. So as we replace our dm with lambda dx, then what we get is our 2m over L squared x dx times the original x squared that's in the problem from the r squared here. And our limits of integration are going to go from the end, right? They said from the end of the rod, about the end, from 0 to L then. All right, so we pull our constant out, 2m over L squared. And then what we're just integrating is a cubic. So you can see on these exams, most of the time you're integrating a polynomial. They just want to see if you can, set this up and finish this out. So the integral of x cubed dx is x to the 4th over 4, and we're integrating from 0 to L. So substituting the L in for the x, we end up proving that the moment of inertia is the 1/2 ml squared. All right, and that's true for a triangle there, that triangular shape with that linear mass density. So there we go. Okay, so moving on, you can see how they award the points. They just want you to be able to know that you need to use that expression, so you get 1 point for just being able to copy that really pretty much right off your equation sheet. Then correctly substituting the linear mass density for the dm expression. All right, they give you a point. And then for actually being able to come up with the correct answer, you get a point. So even if you screw up the integral somewhere, you can get 2 points for just getting everything set up right. All right, so that was part A. Part B, now they want the total moment of inertia of the hoop and the 3 of those rods on the inside. So remember, that moment of inertia is just like mass. It's just summative. So we just need the moment of inertia plus 3 of the rods. So for a hoop, remember it's the mass of the hoop times the radius of the hoop squared. And then 3 times, we just found the expression for the moment of inertia of a rod is 1/2 mass of the rod, length of the rod squared. So since the mass of the hoop is equal to the mass of the rod, that's stated in the problem, all right, so we'll just let that equal m. And the radius of the hoop is the same as the length of the rod, and we'll just let that be L. And by the way, they told you that the rotational inertia about the center for the thin hoop is ml squared, so you didn't have to have that memorized. All right, well now it's just a simple summing of these together. So we have the moment of inertia of the hoop plus the 3 times the moment of inertia of the spokes about their end, and we add that up and we get the 5/2 ml squared. All right, so if you take a look at how they awarded points on this one, same exact thing, 1 point for just realizing that you need to sum them all up, and then another point for the correct answer. So you can see that even if you make an algebra mistake in here, as long as you show the expression and write down what you have, if you didn't get the right answer, you can at least get a point for knowing what you had to do. So you just have to make sure you're clearly communicating each step. Write your equation, show your substitution, and show your answer. All right, part C. So part C is getting at the idea of applying a torque. So it says the hoop rod's system is initially at rest, but held in place, but is free to rotate about its center, and a constant force F is exerted tangent to the hoop for some time delta t. All right, whenever you see a force and you see the time delta t, you should always think, just like if you saw F and delta x being work, F and delta t means an impulse. And the big idea here that we've learned is that forces for times indicate an impulse or a change in momentum of the system. Since we're dealing with an angular system, the expression for an angular impulse was torque times the delta t equals the change in the angular momentum. All right, so when you apply a force or a torque out here at the end, you're going to change the angular momentum. All right, if it was F and theta, right, then we could think about changing the angular kinetic energy. But in this case, it's F and t. All right, so using that idea and using that equation, should be on your equation sheet, we just have the torque will be R times F delta t, and the change in angular momentum is I omega final minus I omega initial. So we know that in this case, the radius of the hoop is L. So we can start to do our substitution in here. We have RF delta t and 5/2 m L squared. So this is our I, right? Omega F starts from rest. And then substituting the L in for the R in this expression here, and just doing the algebra through, we come up with an expression for the final angular speed in terms of the quantities they wanted. So it's important that you end up just in terms of the quantities that they wanted. So again, understanding that you need to use this expression, you get a point. Okay. Then for relating the lever arm to the length of the rod, you get another point. So just for understanding that L is equal to R and substituting it in, they're giving you a point, and then a correct substitution from part B for whatever I you came up with leads to this expression. Now let's say you derived the wrong I, or the I expression wasn't the same. You won't lose this point. As long as everything is consistent, you don't get double jeopardy, so you'll still get full credit if you at least you use your I from part B. All right, so let's take a look at part D. So part D is looking at energy, obviously, whenever you're going to change an object's height up a ramp. A lot of times you're thinking about energy, but first of all, they want to bring forces into this and free body diagrams. So free body diagrams are usually at least somewhere on the test once or twice. So one thing that's interesting about spinning objects and ramps and rolling is this term without slipping. So when an object is going without slipping, okay, then we can realize that friction is going to be part of the problem. So that might not be quite apparent to you. Obviously, you're going to think about gravity right away, the normal force of the ramp. But the idea is when we've had objects slide up ramps before, like blocks, they were usually frictionless or they had friction, right? We didn't have to think about what happens when an object rolls up a ramp. So when we go to draw our FBD, we'd have gravity straight down, label it, right? You have the normal force perpendicular upwards, right, to the ramp, and there's a force of friction up the ramp. All right, so when we think about that force of friction, without slipping indicates that there must be friction. So think about, could you drive up an icy hill, okay, if there was no friction, right? So the friction on the wheel is from the ramp on the tire. All right, so if the tire is rolling this way, then friction is going to be opposing that direction of the rotation to keep it from slipping. All right. So that one might be a little bit subtle, and you probably have not thought about that frictional force at all. So that one might have been a little bit tricky, but that's what the without slipping thing indicates. All right. So notice that even if you forgot that frictional force, it all is not lost. You still get 2 out of the 3 points. So at least knowing the normal force is perpendicular and the weight is straight downward is what you need to do. So you got to justify these as well in the problem. So notice that it does ask you to justify them. So using that idea of the normal force being perpendicular, they're looking for that idea, right? That you've studied that and that you know that. And that knowing that the gravitational force is always vertically downward, right? You don't want to draw the components along the ramp or anything like that. You just want to draw that gravity force straight downward. And then knowing that the friction would be the opposite direction on the tire for the rotation. You're driving up the ramp, right? Or going up the ramp, then that would be another point there. But if you could at least get 2 out of 3, like I say, if you forgot friction or you hadn't thought about it. All right, but that's the FBD. Okay, and then the last part of the problem is using the idea of energy on the ramp. And so it says derive the expression for the change in height to the center of the hoop, right, from the moment it reaches the bottom of the ramp to the moment it reaches its maximum height. So we've done this kind of problem with blocks and things like that before. So since there's no slipping in these cases, there's no rotational work done by the force of friction, even though we have friction on it, and friction usually does non-conservative work. If you think about it, and this is another subtle point, if the tire's not slipping, okay, and the delta S that would move through that force of friction would usually be the rotational work or torque done. But since the wheel doesn't slip, the force of friction doesn't do any work. There's no delta S for the force of friction part of it. If you think about it, now it's a moving frame of reference, so that's kind of a hard thing to think about as well. But if you want to think about it in other types of terms, there'll be no frictional heat loss, right? I mean, if the surfaces, if there's not going to be any rubbing between the surfaces because there's no slipping, there won't be any energy loss to friction, and maybe that's the easiest way to think about it. So in this case, when there's no slipping, energy is conserved and there won't be any work done by a non-conservative force in this case. So our total mechanical energy initial should equal our total mechanical energy final, just like we've always done the conservation of energy problems. So what is that? Okay, so you always think about potential energy. In this case, we have translational kinetic energy and we have rotational kinetic energy. And we should have those same 3 forms of mechanical energy at the top. So let our initial height be 0. We're on the level. And then it says going to a maximum height here, right? So notice that if you're at a maximum height, what they're telling us is that's where our translational velocity becomes 0 and our angular velocity would be 0. So simplifying our mechanical energy formula, we just have the 2 kinetic energy expressions equals the final potential energy at the end. So now we just have to do some substitution. Now, don't go too far with this, because if you read the question carefully, you can save yourself a lot of work. Notice that they show the expression, the answer in the terms that they want. All right, I total is one of the expressions you can use. So we don't have to substitute in what we found before. We can leave I total in that final expression. That's going to save you some time. All right, so if we come down and we do that and we start doing substitutions, our total mass, right, for our kinetic energy is the hoop, right, plus the 3 rods. So that's a total mass of 4m. So we have the 1/2 times 4m vi squared, 1/2 I, right, the total I, omega I squared, and our 4m GHF. So we're going to leave this the same. Knowing that this initial velocity, right, since it's a rolling object, is our r omega, then we can, and our r is equal to the, again, the length of one of the rods. We can express that in terms of our L omega I. And again, that's one of the constants that they're saying that you can use. Notice that they don't have r as one of these values. So making r equal to that L is kind of important to getting down to your the terms that they're looking for in terms of all of this stuff. All right, so just making our substitutions, and then basically it's algebra from here on out. What I like to do when I have fractions in a case like this is just multiply the whole thing through to get rid of the fraction. So I just multiply each term by 2. I come up with this expression, and then finally just simplify it. I pull a omega I out, and then divide by 8 mg, and then that gives you your expression for the final height in terms of all the things they said that you can leave it in. Okay, so what's their point distribution for this one? Okay, for understanding that you have both linear and rotational kinetic energy in the equation for conservation of energy, they give you a point for that. Okay, so for understanding that expression, so you want to write these things down, and then you get another point for the correct substitution. So this one's really interesting, isn't it? For realizing that translational velocity is r omega, and substituting then right L omega for that, then you get the another point for doing that. And then finally working it down and getting the right algebra. So getting to the end is going to be your last point. Okay, so again, notice that you might say, so why didn't they have us put in anything for the expression for the I total? It's probably mostly a grading thing for them, because if you got the wrong answer in B, then they'd have to try to figure out in your final answer where you went wrong. So they just let everybody use the same I total, and then everyone's going to realize it's 4 times the mass, and that helps them come up with an expression during their grading. So the only reason that I can see that they wouldn't have you substitute in the expression that you figured out, the 5/2 ml squared for the I total, is for that reason. It simplifies their grading. That way they can award points and don't do double jeopardy in a much more efficient way. All right, so anyway, that's a look at a rotation problem, and hopefully that helps.